Okay, hello everybody. Welcome to lecture number 2 in MA 283 linear algebra. So this is partly an introductory lecture, and we'll also have a look at section 1.2 of the lecture notes. But I wanted to say some general things about the course first of all, and if anyone has a question, please either put it in the chat or feel free to turn on your microphone and ask one. I'm going to share a couple of things, and first of all, I'm going to share our course website, if I can. So there it is. Okay, so hopefully you can see that. So the URL for this website is shared already in the emails that have been shared. If anyone can't see it, please put a note in the chat or complain loudly. So this is where our resources will basically be. So it's the address is rkq.ie teaching MA 283 linear algebra. So just to sort of nuts and bolts, first of all, this is the front page. We will have various resources that will be updated here from time to time and week to week as we proceed through the course. In particular, we'll have a kind of weekly sub-page for each week. So week 1 is currently up. We'll come to that in a second. Our lectures as of next week will be in person on Wednesdays at 1 o'clock in G002 in RSC Cahill, and on Fridays at 11 at this time in the Darcy Thompson Lecture Theatre. So I just want to make a comment about that. Obviously, we're still living in quite a difficult period with regard to the COVID-19 pandemic, and a lot of people are having to isolate currently in case numbers are extremely high. We all know that. So lectures are in person. I'm not insisting that everybody or anybody attends in person, and I will be posting as well as running lectures in person. I'll be posting recordings of lectures each week, probably pre-recordings. I won't attempt to record the live lectures, I think, but I'll post pre-recorded versions of them, and I'll try my best to keep up to date with that. If anybody is concerned about lectures in person or lectures online, please feel free to get in touch with me. I think we have to do our best to try to be flexible because of the different and sometimes difficult circumstances that everybody is dealing with. So I wanted to make a couple of comments about it. And in particular, I want to say that if somebody is not in a position to attend lectures in person, I am sympathetic to that, and I won't assume that it means you're not participating in the course or that you're not in touch. And please, especially if you're in that situation, please do keep in touch with me and let me know how you're getting on. And in general, because we are in this still difficult situation, which is likely to persist for at least a few more weeks, I'd be interested in your feedback on how things are going for you with the kind of constraints that we're dealing with. And I'll say more about that next week. And we'll have some channels for feedback, either anonymously or not, at any stage during the course. So anyway, the plan next week is we will hold our lectures in person. Obviously, we'll observe all the safety precautions and do our best to manage as best we can. Yeah, somebody had a question there? No, okay, okay. So that's the plan. We will also have tutorials, and they will commence in week 3. And the tutor for our tutorials will be Victoria Sanchez Munoz, who is a postgraduate PhD student in the School of Maths. She was also the tutor for this course last year, and I'm sure that you will enjoy working with Victoria. Okay, so our syllabus outline. I mean, I guess many people have probably already watched the first lecture, or if you haven't, you probably will have a chance to do so hopefully soon. What are we doing? Well, this course is really sort of our first sort of comprehensive introduction to linear algebra. And I know that you started studying linear algebra last year also, with Graham in particular. But this is a more, I suppose, sort of theoretical and more comprehensive and hopefully extensive introduction to linear algebra. So linear algebra, I think it's fair to say, is really kind of one of the most important areas of work within the entire field of the mathematical sciences. Whether you're a mathematician who's interested in sort of questions of pure geometry or pure algebra, or whether you're an applied mathematician interested in modeling almost any situation, or if you're interested in data and statistics, it's extremely likely that linear algebra would be really one of the sort of fundamental kind of backbones of what you do. So linear algebra is the theory of vector spaces. If you've had a chance to look at the first lecture, you probably have a sense of what a vector space is. If you haven't, don't worry about it, because we will be encountering them many times throughout the course. And I suppose the other sort of, so technically and theoretically, that's what it is. It's the study of vector spaces, which are abstractly defined algebraic structures, but which also are extremely prevalent in all areas of mathematics, and we are familiar with sort of many examples of them. So we'll talk shortly again about what a vector space is and how to recognize them when you meet them. But also, an awful lot of the machinery and theory of linear algebra can be communicated using the algebra of matrices, which is something a bit more concrete. So matrices, as you know, are arrays of numbers that have algebraic operations associated with them. And so in a sense, kind of matrices are kind of a scheme for encoding many of the problems of linear algebra. And a lot of the work in linear algebra is to do with sort of moving between kind of matrix settings and maybe more abstract or theoretical settings. So we'll have 4 chapters in our syllabus. The first chapter, which is the one we're in now, is just called, it's kind of a preview of the whole course in a way, but we're going to try to sort of figure out what is linear algebra about, what are the themes, what are the big concepts. So one of them is vector spaces. And the definition of a vector space was basically the theme of the first lecture, which was recorded and is available. It's an important lecture, but the second lecture and the subsequent ones don't immediately depend on it. So if you haven't had a chance to look at that one already, don't worry. It's not really necessary for the next couple of lectures, but it is one of the sort of key elements and key ingredients of our whole course. So do have a look at it at some stage. Okay, the next thing we're going to do is have a look again at matrices and a review of matrix algebra. So we'll start that today and we'll continue it next Wednesday. And then the other thing that we'll talk about in chapter 1 is general schemes for solving systems of linear equations using the algebra of matrices. So systems of linear equations are what are referred to often in the post-primary syllabus as simultaneous equations, where you've got a bunch of equations and you want to find simultaneous solutions. And so we're going to give an account of a sort of a systematic scheme for solving such systems, which allows us to deal with systems with many equations and many variables. And that scheme is so-called Gauss-Jordan elimination. And that will be the third ingredient of this first chapter. So with that behind us, our definition and examples of vector spaces, our review of matrix algebra, and our study of linear systems, we would be in a good position really to kind of build up the theory of linear algebra. So in chapter 2, we're going to be talking about vector spaces and their sort of key structural properties and things that you can do with them. So I suppose chapter 2 is kind of what I think of as being really kind of the core of the fundamental theory of linear algebra that arises in absolutely every area of mathematical work. So whether you're interested in linear algebra for its own sake or not, I think as you kind of proceed with your mathematical life, the content of chapter 2 is really going to be important for everyone to know, whether the person is a statistician or a physicist or an applied mathematician or a mathematical modeler or a geometer or a topologist or whatever. You need to know about vector spaces and linear transformations. So that would be quite important for us. And we'll try to kind of keep track of important applications and sort of practical realizations of these concepts, while we also explore the abstract concepts themselves. The third chapter is about eigenvalues, eigenvectors, and the concept of similarity for matrices. And I suppose we'll say more about this at the time. I know that you already have studied eigenvalues and eigenvectors, but we'll be interested not only in kind of calculating these things, but also in how to interpret their meaning and what they have to do with the content of chapter 2. And then the fourth chapter, we'll talk about orthogonality and inner products, but we'll come to that a bit later. And we'll talk about that when the time comes. Okay, so that's kind of a very rough, possibly not terribly informative at this stage, summary of the syllabus, but that's what we'll be at. And I guess the 4 chapters kind of more or less correspond to probably a quarter each of the content, roughly. Hopefully it'll work out that way. And so we can think of the course as being sort of divided into 4 chunks. All of it depends on the first and second chapters. This is really where the fundamentally important stuff is. Okay. Anybody have a comment or a question? Okay, so then we have lecture notes, which are in the process of being developed. I will try to keep them up to date as best I can. Apologies in advance for any failures in that regard, but they will be posted from week to week as we proceed. So at the moment, the first 2 sections of the lecture notes from chapter 1 are there. And we can click on these links to see them. So the first section there basically more or less corresponds to the first lecture, which is the one that was scheduled for Wednesday and was pre-recorded. Section 1.2 corresponds kind of partly to today's lecture and probably the next one as well. And so, yeah, lecture notes will be assembled here by sections. Please do give me some feedback if you have some. The lecture notes are under construction. There's a high probability that they will have plenty of typos. So if you notice any, I would be very grateful to you if you can let me know about them, and I'll try to correct them as I become aware of them. And indeed, I'll keep an eye out for them myself as well. Okay, I wanted to say a word about the assessment, because that is obviously a question that is important for our practical activities. So as usual, we'll have a combination of different elements in the assessment. So we'll have 4 homework assignments, basically one corresponding to each chapter of the lecture notes, pretty much into each chapter of the course. They'll be run on web work, which means that they're run online, which has, as you know, advantages and disadvantages. And the advantage, I suppose, is that you get quick feedback. The disadvantage is it's not the same level of communication between human beings that we would ideally like. But that's how we do it. We will have a 2-hour final exam in the summer exam session, which will account for, in principle, up to 70% of the marks. And we'll have a third element as well, which is a kind of an optional bonus. You're not required to do it, but I really hope that many of you will be interested. So we'll have 10 weekly challenges as we proceed through the course. And they'll be run on Blackboard as Blackboard assignments. So, and they will account for up to 20%. So I'm sure you're already wondering how this adds up to 100, but don't worry, we'll come to that in a second. So the 10 weekly challenges will start next week. And basically what each challenge will do is it will ask you to come up with some interesting example of something with some specified properties. And so each week there'll be an opportunity to submit a response, if you want to the weekly challenge. And submissions will be marked out of 10 points. And basically 5 of the 10 points would be sort of for the mathematical content and accuracy of your example and its relevance to what was asked. And the other 5 are sort of for, well, I've said for creativity and quality of exposition, but basically for, you know, how well you've communicated your idea. So you can score up to 10 points for each weekly challenge. Each of them is worth 2%, so 10 out of 10 is 2% in your course mark, and so there's 20% in total. You don't have to do all of them. You don't have to do any of them. You can do them according to your interests and when you have time on your hands and whatever. They're not, you know, they're not obligatory. But I hope you might enjoy them. So please don't feel obliged to do them. They're not meant to be a pressure thing. They're meant to be a sort of an interesting thing for people who enjoy such things. And so basically, if somebody does the 4 homeworks and the final exam and the weekly challenges, that means that potentially they can score up to 120 points in the course. And so if they do score more than 100, their score would be rounded down to 100. But basically, so like if you do the homework assignments and the weekly challenges and the final exam, and your scores on all 3 of those elements add up to kind of 90, let's say, out of 120, then your mark in the course will be 90. Okay, so basically, the weekly challenges are an extra bonus. None of the elements are completely mandatory. I hope you'll do them all, but they're not mandatory. And the challenges in particular are sort of presented as being an optional bonus if you want to participate. So basically, that's how they'll be. So, you know, as we proceed through the course, we'll meet lots of different types of objects that have different properties. And one of the skills, I think, for mathematicians is to be able to kind of come up with interesting examples that demonstrate properties and non-properties, or properties that some things have or don't have, that kind of highlight some of the key concepts. So I think it is an interesting and enjoyable skill to kind of get into the habit of, you know, making up nice examples that capture certain things. So every week, the weekly challenge will be, you know, give an example of a vector space that has this property but not that property, or whatever, something like this. Give an example of a matrix that has some interesting property. Make up an example of an application of some concept that we saw in the course, or some scenario that sort of illustrates the concept. Okay, so that's how they'll be. There's no limit in terms of what you can do. So, you know, you can upload a handwritten note as your answer. You can upload a typed note. You can create something else if you want, an animation or a video or something if you want to upload for a weekly challenge. And that's how the format is flexible, and you are invited in particular to exercise your creativity with the weekly challenges. The first one will be based on an example that we'll hopefully meet in today's lecture, and it will be posted in the next day or two. So that'll be sort of the first of our 10 weekly challenges, and it'll be open for 10 days or so on Blackboard. Okay, that is some remarks about the assessment. If anyone has a comment, please feel free to put one into the chat or to turn on your microphone. No comments yet, so I take that to mean that things are sort of relatively okay so far, but if not, please do raise a question if you have one, or insert a comment in the chat. That's our plan. The tutorials will begin in week 3, I think I mentioned that, and the first homework assignment will hopefully open next week, but I need to get the web work up and running, which will happen early next week. Okay, just the links then from this page. So the weekly content will be posted from week to week, so I'll just click on the week 1 content. So basically what's there is a kind of summary. It's like, it's for most people, I think we're in the MA 180 or 190 course last year, and we already met there. Hopefully we'll actually meet in person this time, which I'm very much looking forward to. But the structure is the same. Each week we'll have a page that will have kind of a summary of the main themes for that week, and we'll have the whatever recordings and slides and whatever we have from week to week will be there, and the relevant sections of the lecture notes will be highlighted. So that's the page for week 1. Wednesday's lecture is there, and today's lecture will be posted there after the recording is finished. So that's the plan. That's kind of how our online resources will be managed. And I'll, as I said, do my best to keep it up to date from week to week. One comment about the lecture notes, which are linked here from the main page, is that as with MA 180 last year, if you were in that class, if you weren't, don't worry, we'll all get to know each other quickly, is that the lecture notes generally have a bit more detail and a bit more kind of detailed exposition than what we can put into the slides from the lectures. And they have a few examples that are not they won't be discussed in lectures. They're just a bit more, there's a bit more sort of extensive text there than what we have time for in a 45-minute lecture. So, of course, how you make use of all the resources is a matter for yourself. And everyone knows themselves how they best learn and how they best use resources. So I'm not prescribing anything there, but I would just say, even if your preference is to kind of maintain your own set of lecture notes, which some people like to do, don't ignore the lecture notes anyway, because they do have some content that isn't necessarily discussed in the slides. So the slides are not a substitute for the lecture notes. They're really just a kind of they're a fairly sort of skeletal summary. So make sure that you don't ignore the lecture notes, even if you're also maintaining your own set of lecture notes, which obviously might be something that works well for a lot of people. Okay, anybody have a comment or a question at this point? I'm going to actually just pause the recording for a second in case Okay, so that brings us to our first, our second lecture, but our lecture content for today. So this is section 1.2, corresponds to section 1.2 of the lecture notes. It's lecture number 2, and it's a review of matrix algebra. So in this section, I expect that many things will be familiar to many people, but probably not everything. So we'll have a look at what we know about the algebra of matrices, and this is going to be really our sort of bread and butter in this course. We're going to need to be familiar with the operations of matrix algebra. So okay, so as we know, a m by n matrix over a field is an array of m rows and n columns whose entries are elements of our field. Okay, so if you didn't get a chance to look at the first lecture and you are not familiar with the word field in this context, do not worry. Just think about F as being the field of real numbers. So F is the system of real numbers. A m by n matrix over a field F, so over the real numbers, for instance, is an array of m rows and n columns. So for example, a 3 by 4 matrix over the real numbers would be something that has 3 rows and 4 columns, and every entry would be a real number. So it's like 4 entries in every row. Like it could have 3, 1, 0, 2 in the first row, minus 2, 0, 1, 4 in the second row, minus 16, 1, minus 2, 1000 in the third row. That would be an example of a 3 by 4 matrix, which we would write, we'd say that it's over the real numbers to mean that the entries of the matrix are elements of the set of real numbers. Okay, so I guess we know that. So this is not news to anyone, but I guess a few of the things that you could potentially get wrong here if you're not careful are, you could get confused about which is the m and which is the n. So if it's 3 by 4, this is just a convention, but it's important that we're consistent with it. So 3 by 4 means 3 rows and 4 columns. And that's just the sort of agreed convention. Of course, it would make equally good sense to do it the other way, but this is how we do it. Okay, so I think that's kind of the main thing that that we could sort of get confused about here, and we must use our notation consistently so that we all understand each other. Okay, and so the other remark is just that this sort of expression m by n is referred to as the size of the matrix. Okay, and that's a bit of lingo in the language of matrices, that if a matrix is like 2 by 3, we say that its size is 2 by 3. In my opinion, it's not really a very good word, because it really describes the shape of the rectangular array more than the size of it. But the word size is the word that is used, and we're not going to change that at this stage because the language is so well established. Okay, so yeah, so the size, if somebody talks about the size of the matrix, what they mean is the number of rows and the number of columns. Okay, so second remark, and here again, if you're not sure about this field F, just replace every appearance of F with the field R of real numbers, the set of R of real numbers, and you'll be fine. We'll come back to the concept of a general field at various stages. Okay, so the assertion is that the set of m by n matrices over the real numbers, for instance, is a vector space. And remember what it means to be a vector space, or if you haven't had a chance to look at first lecture yet, let me very briefly say what it means to say that this is a vector space. So it means that its elements can be added together which is certainly true if we take the set of all m by n matrices where m and n are fixed now. So we're talking about, like, let's say all 2 by 3 matrices over the real numbers. We can add together two 2 by 3 matrices and get a new 2 by 3 matrix. They can be subtracted from each other, and they can be multiplied by scalars. So a vector space is a structure, a set of objects, some sort of mathematical objects, whose elements can be added together, subtracted from each other, or multiplied by scalars. And the scalars in this context are the elements of the field that you're working over, which for us, let's say for the moment, by default, is the field of real numbers. So a scalar here would be a real number. Okay, so so a vector space in general is any structure, basically, okay, with some extra rules, where you have the properties that the elements can be added together or subtracted from each other or multiplied by scalars. And so in order to talk about vector spaces, you have to already have a system of scalars in mind. It can be the real numbers or the rational numbers or the complex numbers or some other number system, which is the field that's referred to. Okay, so the assertion here is that the set of m by n matrices over a field F. Oh yeah, sorry, I should have said what that is actually. I didn't introduce that notation. So this is the set of all m by n matrices over the field F, which could be the real numbers. So yeah, so we have to kind of first justify that assertion. So two matrices can be added together if they have the same size. In this case, their sum is just the thing that you get by adding the entries in all the positions. So for example, if we want to just give an example of that, if we're working, let's say, in the 2 by 3 matrices over the real numbers, the claim is that if we take a pair of 2 by 3 matrices, we can add them together and get a 2 by 3 matrix as the result. So let's say we do it, we get, here's one 2 by 3 matrix, here's another one. And the point here is the m and n are fixed. We're not talking about all matrices over the real numbers. We're talking about all matrices of a particular size. So our size is 2 by 3. So here's another example. Let's say we have 2, 0 in the first column, minus 3, 1 in the second, 0, 4 in the third. Then the sum of those two matrices, the way we define it is just we say, well, we add entries in the same position. So in the top left position, we have 1 plus 2. That's 3, 2 plus minus 3, minus 1 plus 0 in the top right. In the lower left, we have 4 plus 0. Lower center, we have 0 plus 1, and 3 plus 4 in the lower right. So that's the sum of those two matrices. So certainly, yeah, okay, no, nothing too surprising there. We can do that. And the result is a 2 by 3 matrix again. And of course, if you wanted to subtract instead of add, there's nothing nothing too surprising. We just do the same thing, except we subtract entries in corresponding positions. So and again, so the sum or difference of a pair of 2 by 3 matrices is again a 2 by 3 matrix. Okay, fine. That's not the most profound thing we're going to say in this course, but it's something that has to be noted. Okay, a few other remarks about this whole business. The m by n zero matrix is the m by n matrix whose entries are all 0. Okay, so why are we highlighting that? The reason for highlighting that is because the m by n zero matrix, which is the m by n matrix with entries all 0, so we might denote it by 0 with a subscript of the size of our matrices, whatever they are. So the 2 by 3 0 matrix, which we might write as 0 subscript 2 by 3, is the matrix that has 6 zeros arranged in 2 rows of 3. Okay, so it's the identity element for addition of n by n matrices. This term identity element is something that you'll meet many times in algebra and in mathematics. What that means is that if we add that particular matrix to any other matrix, we have no effect on that other one because we're just adding 0 to each entry. So we don't change any of the entries. Okay, so it's just, I suppose we're just noting here that we have this identity element for addition, which is the 0 matrix. We will use the term 0 matrix very frequently, so we need to have it in our vocabulary. And the other remark, I guess, is that the negative of a matrix so this is again nothing that would surprise anyone. But if A, for instance, let's take a 2 by 2 example, the matrix with entries 1, 3, well, let's say 1 minus 3, 4, 2. Write that a bit more legibly. So let's say that if A is a 2 by 2 matrix with entries 1 minus 3, 4, 2, then its negative is written as minus A, and it's the matrix whose entries are -1, 3, -4, -2, just the negatives of the entries of A. And then the relationship that A and its negative have in common is that when you add them together, you get the zero matrix of the relevant size. And this is basically the sort of machinery, the algebraic machinery that enables subtraction. If you want to subtract one matrix from something, you're adding the negative of that matrix, just exactly as we do for numbers. So basically, once we have addition and we have a zero element and we have negatives for everything, then we also have subtraction. Okay, that's final comment. This is to verify that this space of all m by n matrices is indeed a vector space. A matrix can be multiplied by a scalar. That's part of the required machinery to have in order for something to qualify for the title of a vector space. If we want to multiply a matrix by a scalar, that means multiplying it by a number. Okay, so the entries of the matrix are numbers that come from the set of scalars that we're working with. And so to multiply a matrix by a scalar means multiplying every entry of the matrix by that scalar. And with these operations of addition and scalar multiplication, the assertion is that the set of m by n matrices over the real numbers, but over any field, is a vector space. So example of scalar multiplication is if you take a matrix with entries 1, 0, 2, 1, -2, 4, and you want to multiply it by the scalar 3, well, all you do is multiply each of the entries by 3. So you get 3, 0, 6, 3, -6, 12. Okay, so these are kind of the basic operations in a vector space. A vector space is any system in which you can add elements together, subtract them. You always have a zero element and negatives for everything. And you can multiply by scalars. So further examples include things like the space of all functions from the real numbers to the real numbers is another example of a vector space. We can add functions together to get new functions. We can multiply functions by scalars. The space of all polynomials of degree up to 5 over the rational numbers, let's say, with coefficients in the rational numbers, again, is an example of a vector space. We can add polynomials of degree up to 5 together. We still get objects of the same type. We can subtract them. We still have a polynomial whose degree is at most 5. We can multiply polynomials by scalars from the set of numbers that the coefficients come from, and we have another vector space there. So we're going to see the term vector space, in lots of different sort of manifestations in different examples. And so if what I just said only makes kind of, if it's not completely familiar to you, don't worry, we'll be seeing lots of examples and lots of different kinds of examples. So, and there are some in the first lecture. Okay, so the example here was going to be the ones that we just looked at. So, okay, the other kind of key feature of matrix algebra, which is not as obvious in terms of how it works, is matrix multiplication. So I know that you're familiar already with the processes of multiplying matrices from your work last year. Matrix multiplication is a really important operation in linear algebra, but also in all the areas where linear algebra is applied to. And it's defined in a way that is not necessarily obvious, and it's not necessarily what you might first guess. So, we've seen just now, and if it's not news to you, that if you want to add matrices together, they have to have the same size, and you just add entries in corresponding positions. If they have the same size, if they don't have the same size, you can't add them. Like you can't add a 2 by 2 matrix to a 3 by 3 matrix. You just can't do it. Okay, there's no definition of that. There's no concept of that. But if two matrices have the same size, you can add them kind of in the obvious way by just adding entries in the same positions. So like if you were doing that and somebody said, okay, well, how would you multiply matrices? I mean, I think honestly, most people's first guess would be that you'd say, well, you can only do it if they have the same size, and you just multiply entries in corresponding positions, like you define addition. That would be kind of a sensible way maybe to define matrix multiplication. It's not how we do it. And the reason why it's not how we do it is because matrix multiplication sort of captures certain properties relating to the rows and columns of the matrices that aren't captured at the level of the entries themselves. Okay, so I mean, what I just described is some kind of version of matrix multiplication, but it's not. But it's something else. It's a different operation. It's not matrix multiplication. So the way that matrices actually are multiplied is more complicated than that. The situations in which it applies are also more complicated. So if somebody hands you two matrices, you may be able to multiply them and you may not, but it doesn't depend on whether they have the same size as each other or not. That's not the compatibility condition that they need to satisfy. What they need to satisfy is that the number of elements in a row of the first matrix has to be equal to the number of elements in a column of the second matrix. If that happens, you can multiply them. And that's another way of saying, of course, that the number of columns in the first matrix has to be equal to the number of rows in the second one. So let's see how matrices are multiplied. And also, one thing that I want to kind of emphasize, I guess, in this first lecture, or additional lectures is why this definition makes sense and how it actually does correspond to sensible operations in real life. Because one of the things that sometimes does happen is that matrix multiplication is presented by saying, okay, here's a pair of matrices, here's how you multiply them. You take a row of one and a column of the other one, and you sort of combine them in some way. And it's not really obvious often, in my experience at least, why this is actually a sensible thing to do, or why this is the way that this operation will be defined. So let's try to figure it out and see a few examples to maybe kind of try to justify it. Okay, so here's a definition. This is a definition, a really important definition in linear algebra generally, which absolutely needs to be part of our vocabulary. So highlight it for that reason, as well as for the reason that we need it now. So supposing that we have some elements of a vector space. So if you don't like abstract vector spaces, think of them as being column vectors or as being matrices of the same size. Okay, so we've got a bunch of elements, v1 to vk. They live in some vector space. Okay, that means we can add them together and we still get elements of this vector space. Okay, and the vector space is written over a field f. So think of f as being the field R of real numbers, if you like, to put your feet on the ground a little bit. Okay, so a linear combination, or a f linear combination, but that's just, usually you can just call it a linear combination. A linear combination of these k elements is anything that you can get by multiplying each of the k elements by a scalar from your field, so by a real number, and then by adding up the results. Okay, so if v1 up to vk are all, for example, let's say column vectors of length 3, which are 3 by 1 matrices, then what it means to talk about a linear combination of them is something that you can get by multiplying each of them by a scalar and then adding up the results. Okay, so typo there. So it's not necessarily obvious. Like if I give you 5 different 2 by 2 matrices, it's not going to be obvious by glancing at them whether the 5th one is a linear combination of the first 4 or not. Okay, it might be, it might not be, it might not be that easy to sort of decide the answer to that question. But if I give you 4 matrices, then a linear combination of those 4 is anything that you can get by multiplying each of them by some scalar of your choice and adding the results together. So it'll still be a 2 by 2 matrix. Okay, that's the general concept of a linear combination, and we'll see a couple of examples in a minute, and some and we'll see them throughout. But yeah, I suppose this term linear combination is one that is worth kind of revisiting and making sure that you understand it well. Okay, another bit of this is kind of more straightforward terminology rather than introducing the concept. A column vector is a matrix that is just one column, so it's like a m by 1 matrix. So that's fine. A matrix can have just one column. A row vector is a matrix with just one row. So a row vector is a 1 by n matrix. It has one row and whatever number of columns. A 1 by n matrix. So it's a long, wide matrix. A column vector is a high, skinny matrix. Okay, and then the definition 4 here is really kind of the important one. So before we define matrix multiplication, even though I know that you've already worked with it, we're going to define what it means to multiply a matrix on the right by just a column vector. So if we have a m by n matrix, okay, and we have a column vector with n entries, so A is m by n, V is a column vector with n entries, so it's a n by 1 column. Okay, so A has n columns, each with m entries. V has 1 column with n entries. Okay, then the product AV, which is referred to as a matrix vector product because it's a matrix multiplying by a column vector, but it's a special case also of a matrix product. The matrix vector product A multiplied by V is the column vector that you get by taking the linear combination of the columns of A, column 1, column 2, column 3, as far as column n, whose coefficients are the entries of the vector V, which is the thing on the right in the product AV. Okay, so it's a column vector with m entries, I assert. Okay, so this is a bit of a mouthful, and we've had a couple of definitions there, so let's look at an example of this concept of matrix vector multiplication. So if A, let's give ourselves, A should be m by n, and V should be n by 1, and the n here is the same as the n here. Okay, so let's say that A is, for example, 2 by 4, and then V should be 4 by 1. So we'll give ourselves an example of a 2 by 4 matrix, so it has to have 4 columns with 2 entries each. So let's say we have -2, 1 in the first column, 1, 0 in the second, 3, 4 in the third, and -2, -1 in the fourth, something like that. That's a typical 2 by 4 matrix. And V should be a 4 by 1 column. So let's just give ourselves a column vector with 4 entries. Let's make life easy for ourselves by keeping them not too big. Let's say 1, -2, 3, 1, something like that. Okay, so that's an example. This because -1, so the 4 entries are different. Okay, so that is an example of a 2 by 4 matrix and a column vector with 4 entries. So the claim is that if we want to write down the product AV, so this is a matrix product. Okay, it is it's matrix A multiplied by the matrix V. It's a matrix vector product because V is a single vector. It's a single column vector. So this thing would be referred to as a matrix vector product, but it's also an example of a matrix product. So according to the definition says we should take the 4 columns of A, which are -2, 1, that's the first column of A, 1, 0, which is the second column of A, 3, 4, which is the third column of A, and -2, 1, which is the fourth column of A, -2, -1. Okay, so they are just written down as columns of A. So these are like, oops. These are let me try to write this in a legible way, which is always a bit of a challenge. So these things are the 4 columns of A, written in the order in which they appear in A. And what we are supposed to do with them is take the linear combination of them that you get by taking the coefficients of the entries of V in order to be the coefficients of the 4 columns. So we would get 1 times the first column, -2 times the second one, +3 times the third one, -1 times the fourth one. Okay, so this is an expression for a column in the space of 2 by 1 column vectors over the real numbers, or like, or 2 by 1 matrices over the real numbers, if you like. We know how to multiply matrices by scalars, and we know how to add and subtract them. So we can easily, without much trouble, write down, just do the calculation and write this thing as a single column vector with entries in the real numbers. So in the first entry, we've got 1 times -2, -2 times 1, +3 times 3, -1 times -2. So let me attempt that. We've got -2, -2, that's -4, +9, that's 5, +2, that's 7. So hopefully this is right. If it isn't, somebody complain in the chat. And the second entry, we've got 1 times 1, -2 times 0, so that's 1 so far, +3 times 4, that's 1 + 12, that's 13 so far, +1, which is 14. Okay, so it's an accident that both entries are multiples of 7. That wasn't that was a fluke. That's the matrix product AV. Okay, so basically the definition that I use to think about this is it's the linear combination of the columns of A with whose coefficients are the entries of V. Of course, in practice, in order to calculate it, you can see that what we did in the first entry was we took the 4, let me just highlight them maybe in a different color. We took the 4 entries of the first, oops, sorry, that was supposed to be a different color. We took the 4 entries of the first column of A, so there they are, and here they are again. Sorry, the first row of A, I should say. So there they are. And we multiply them in order by the 1, -2, 3, and -1 of the vector V, which I'll highlight in a different color. So there they are. Those 4 entries, and here they are again. 1, -2, 3, -1. So basically, we got -2 times 1, +1 times -2, +3 times 3, +2 times -1. The entries of the first row of A combined with the entries of the column V by taking the first one's multiplied together, second one's, third one's, fourth one's, and adding them together. So that's kind of typically, I suppose, how we calculate when we do matrix multiplication. We think about combining columns of A with rows of A with columns of V in that sense. But what we're really doing is we're taking the linear combination of the columns of A whose coefficients are the entries of V. And so that means that the result of this matrix vector multiplication is going to be a column whose number of entries is the same as the number of entries in A, because it's a linear combination of the columns of A. So basically, if you have a matrix multiplying a vector, you can only do that multiplication if the number of columns in the matrix is the same as the number of entries in the vector. Okay, equivalently, the number of entries in a row of the matrix, which is the way I like to think about it, is equal to the number of entries in the column. You can only do it in that case, and when you do it, the result is going to be a column which resembles the columns of A in terms of how many entries it has. So it's a column whose number of entries is the same as the number of rows in A. Okay, so that's how matrix vector multiplication works. And even though, like, when we're actually doing calculations, which isn't our only objective, you know, you tend to kind of think about it in terms of combining rows of A with the column V. In terms of what it means, I think it's really useful to think about it in this way of taking the linear combination of the columns of A, whose coefficients come from the vector V. Okay, so that's matrix vector multiplication. Okay, and then the second remark about this, and we'll come back to this when we pick up here on Wednesday next week. But if you want to multiply a pair of matrices together, and using this matrix vector multiplication definition as sort of the basis for that, basically the way to do it is, so let's say we have a pair of matrices A and B. And let's say that A has size m by p for some p, and B has size p by n. So the crucial thing to notice here is that the p, which is the number of entries in a row of A, is equal to the p, which is the number of entries in a column of B. Okay. And if we write V1 down to Vn, V has n columns, sorry, B has n columns, just write them as V1 to Vn. Then what we mean by multiplying the matrix A by the matrix B is basically what we would get by multiplying the matrix A by the columns of B in turn. We've defined how to do that in the last slide and in the last example. So AV1, we know what that is. V1 is the first column of B. AV1 is the linear combination of the columns of A whose coefficients come from the first column of V. AV2 is a linear combination of the elements of the columns of A whose coefficients come from the second column of B. And that thing is the second column of the product AB. So basically, we know how to multiply a matrix by a column now. To multiply a matrix by a matrix, to multiply A by B, multiply A by all the columns of B in turn. The result of each of those is going to be a column with the same number of entries as a column of A, and basically line up those columns side by side. So you've got a matrix then, which has n columns, each with m entries. So you've got an m by n matrix. Okay, m is the number of rows in A, n is the number of columns of B. The p doesn't appear in the size of the product, but it appears kind of in the calculations that you do to compute the product. So that is a kind of reminder, maybe a kind of different viewpoint possibly, about how matrix multiplication works. We're going to pick up here on Wednesday. So our lecture on Wednesday mostly would probably be again devoted to the theme of matrix algebra. And we'll think a bit more about this operation of matrix multiplication, because it's so important in so many areas that we really need to kind of have some good understanding of it, and maybe some different viewpoints are helpful about why it's sensible. So we'll come back to this on Wednesday. If you get a chance in the meantime to think as far as this point, definition 5 in the slides, that would be great. And we'll pick it up there. So thank you very much, everybody. I'm going to stop the recording there. And thanks to everyone who's joining us for the recording.